Okay, I'm going to go ahead and get started here. So, welcome to the NCSA Colloquium Series. We've worked hard to bring in great speakers every week, almost every week, and Abani is no exception to that. I'm very pleased to introduce Professor Abani Patra from the University of Buffalo, who I met in this, I think, in this very room. How many years? What's 2015 minus 2008? Whatever that is, 7 years. 7 years ago, that Merle Giles had organized. So actually, a lot of things are converging here. I think it's really quite an interesting event for us. So Abani is unique and in many ways, but in one particular way, he's the first person to receive a PhD in computational science and applied mathematics. I'm not even sure what the title of the degree is, but it's some combination of those things from the University of Texas. And it was UT Austin was one of the early universities to really get with the program in computational science and actually created a PhD, something that I think Illinois has been at the forefront of for years, but actually still does not have a PhD in computational science, and that's something we might work on. So we have a lot to listen to from Abani, both from his own experience as a graduate student and now as a senior faculty member developing such a program at Buffalo, and I think we'll hear a little bit about that. So Abani went on from UT Austin and got, after his PhD and a postdoc, to become a professor at the University of Buffalo in mechanical and aerospace engineering. And he became a full professor in 2004, and then it was someone after that that I really began to know Abani, starting at this meeting that occurred in 2008 that Merle had organized, and that was really a momentous meeting in my mind. Many things came together, and from industrial partners to computational scientists, academics from many different departments thinking about software environments for the future of innovation, I would say, in America. That was really a very, very important meeting, and I still think a lot about the outcomes of that meeting. So shortly after that meeting, I ended up going to the NSF, and Abani was already a program officer there at the time. And we worked together very closely, and we brainstormed many great things and really bonded together. So we have a very like view about things, and I think Bonnie's going to tell us about how that's evolved over time and what he's doing at Buffalo to develop that. I had one more thing. Oh yeah, I love Abani's title. It's like you take a random number generator and assign it to words in a dictionary and find out how quickly you can come up with a title that actually makes sense. And it seems to have worked. So thanks a lot, Abani.
All right. Well, after that introduction, I'm feeling really good about myself. Thank you. I didn't know I was that good, but thank you. Yeah, the real title is down there, but we started talking about what am I going to talk about, and started writing down things, and that sounded more fun, so that became the title. It's really about how do you do predictive simulations. That's something that I've been struggling with, learning more about as I go along for the last 15, 20 years now. And as I think it was Osborne Reynolds who said, when I meet my maker, I'll finally learn how to do it. But it's an ongoing journey, so that's where we'll do this. Over the course of the years, of course, it's taken an army to work on the things I'll show you. And the NSF has been really nice about paying for most of it. So I thank them in bold letters. OK, so if you were living about 2,000 years ago, and you needed to know what's going to happen in the future, that's what you did. You took your sestereti, and this young lady inhaled some ethane and came up with a prediction. Today, apologies for using the Chinese computer, but heck, they beat blue waters. Sorry. I thought that'd be sensitive to use blue waters here. But today, you go to a big computer and a big data processing facility to do essentially the same thing. Because these have started becoming repositories of our knowledge. They're not just data, they're not just computing, they're now repositories of our knowledge. And that's how we have to start thinking about them. It's not the computing center, it's not the center of computational applications, it's the center of knowledge applications. How do we make that vision real? That's really where we need to go. These are, of course, not new charts to the people in this room. The bottom right is the interesting one. That's the NCAR mass storage growth over the years till about 2010 or so. But that curve is what is important. That's how the data is growing. Bob, wasn't this a good bunch of years we lived in? The Newtonian years, you solved Newton's equations in full glory. As difficult as it was, life was good. Life was good. And that's where the teeth came in. I'll show you now. Oh, I took the teeth out. But all you had to do, and this is how I grew up, solve the equations and it's done. And the equations have all been found by Newton already. And it sort of worked almost. Is one of the first problems I worked on. Difficult problem, but not that bad. If you get to an age where the teeth start going, do not hesitate to do this. These things have become really good now. Okay? These dental implants have really worked. And I was stupid enough in my youth to actually publish it rather than patenting it. So every one of them now looks good. But so this is good. I used adaptive HP mesh, all of that stuff. I solved the equation well, and we got a product out. In about 99 to 2000, this was 98 work, I think, a couple of geologists walked into my room and said, we look at volcanoes. Would you be interested? I said, you mean lava coming out? And they said, yeah, that does happen also. That was the first thing I should have paused. What? You mean that's not the problem? That is not the problem. The problem really in volcanic eruptions, and this kind of shows a picture here, it's twofold. The one that really kills a lot of people is a mass flow. A volcanic eruption will create usually a slurry of mud and debris that comes down at speeds up to 100 miles an hour. That is the one you need to get away from. And then the other stuff that kills people is the very fine, it doesn't kill people, creates a lot of inconvenience, right, Ed? Gets up in the sky and stops planes from flying. I think you had a wonderful 2 weeks in London when the Icelandic eruption happened about 2010, I think, April 2010.
I'll just interject 1 second. There was this great event that I was going to a meeting in London, and I was very, very busy at NSF, so I thought I'll just go for 1 day and I'll come right back and nobody will notice. And my plane was the first one to get canceled when that volcano went off, and it took me almost 2 weeks before I could fly back home. So I got caught.
See, I finally solved the problem. They shouldn't have grounded you, by the way. The British didn't know how to do the calculations right. I can say that in hindsight. But getting back. So this is actually a paper back in 1889. I wish we wrote papers like this now. The language is so colorful. I mean, you almost have to write literature. But anyway, so this is talking about flows, mass flows, and how it moves, how rapid it is. It is essentially a fluid flow at that point, but of course it has very interesting constitutive properties, most of which nobody still really knows. Because you do the calculations, and then you look at the field, and the flow goes about twice as far as it should have gone. So this good days of Newton starting to become a little blurry now. Those equations are not well understood anymore. Now this is a crater lake out in New Zealand. So this was actually 600 million cubic liters of water, acidic water, sitting up in about 18,000 feet high. So it was a matter of time before that thing was going to come down in one big burst. Everybody knew that. So the colleagues down in New Zealand actually instrumented this thing. And I'll play you the movie, if I can figure out how to play the movie here. There you go. And the movie was, they had the instruments, they did everything, that they'll get good data, right? They had a video camera about 50 feet away, thankfully, also. That was the end of the instrumentation. So you got very little real pressure data out of it, but you got a good visual out of it. It's about 3 years of prep. It just, the mass flow of the mud has so much impact force. It just wasn't enough. I mean, somehow that concrete pillar withstood it, but none of the instrumentation really got meaningful data. We got some pressure data, but that was not something we could use. Anyway, this is the ash flow. The picture on the left I really like. It's the lightning that you capture in some of these ash clouds. Here's another one that's very similar. I discovered that once you put tools out in the public domain, you have no idea what people do with them. So I put out this mass flow code and all of this stuff, and I discovered that a Japanese group was using our tools to study a problem in Bhutan on this glacier lake outburst floods. I don't know if you've heard about this thing. So when the glacier comes down, right at the end of the glacier, it dumps the debris, and there is a meltwater lake. Now, these are not tiny. Some of them are really, really big. Then what happens is either there's a landslide event, or what's happening now with global warming. That dam that's holding it back is really a lot of muck and ice. 1 degree rise of temperature weakens that. The civil engineers will tell me better about how quickly that will go. But every now and then, it's like a bucket of water just tips, and you get this big flood coming down. So this nice pristine stream that will be a couple meters across that everybody's jumping across or wading across, suddenly there's a 20-foot torrent of mud and water coming down, kind of like the video I showed you. So this one in Bhutan got attention because it wiped out the king's summer palace. So it got UN attention. And we actually did the calculations. So our tools were being used by that. They hadn't quite modified it. They were using the dry flow tool for a wet flow. They finally had a sensor come and talk to us. So we actually fixed it, and we got some good things out of that. So this is kind of a summary of the kinds of flows we've been looking at. Another big area of concern here is environmental. Mining, anytime you have this gold, silver, and especially heavy metals, you mine them, you create these tailing ponds. So you flush the ore with water, crush it, flush it. So all of that has heavy metals and all kinds of other interesting things that you keep in a dam, a little earthenware dam usually. And then it's supposed to, over time, get back to nature. The one that they're planning to build in Alaska for the Pebble Beach mine, gold mine, that'll be the world's largest gold mine. The dam is supposed to be 700 feet high. Okay, so just think about that in your mind. How much stuff will be behind that? And it's just an earthenware dam. So one day it probably will come down. And you see up here on the top right, that's the one in Hungary that was a copper mine that almost got into the Danube. And that would have been really bad if it hadn't stopped when it did. But fortunately, it stopped about a kilometer away from the Danube after traveling about 40. So that's scary, and the regulatory environment for that is, to put it mildly, weak. The Alaska one so far has been stalled because a particular billionaire has his ranch downstream, and he's bought out enough congressmen to keep it stalled for now. But how long? I don't know. I got consulted. I got a little consultancy on that, and we think it's a terrible thing if they build that. So that's just to show you what we have done over the years. So we have created this tool set, many papers, many pictures. But the nicest thing we did was to put all these tools online. So if you go to this vhub.org, you can use all our tools online. Somewhat limited computing, but if you need more computing, then you can always get to exceed from there. Okay, so the good news about that is I don't have to support a lot of people using my tools. The bad news is I have no idea what they're doing anymore. I did discover a group in Norway had used some of our tools for submarine flows. And of course, the rheology is all wrong. So we have a big announcement saying we're not responsible for your results, please. Anyway, one thing that I should talk a little bit about mechanics. I did promise you mechanics and mathematics. So what has been done in many of these flows is that the reason they're possible without every one of them requiring blue waters is you can depth average them. They're 40, 50 kilometers long, 5, 10 meters deep. That's all. So you can depth average that, and you get pretty good answers, even after depth averaging. And so I'm kind of going over the process for that here. So that's a very standard shallow water type equation that comes up when you do that. The bad news, of course, is that you lose any notion of what's happening in the z direction. So one of the most important things is how it entrains material. And you have to do that in a very superficial way now, because you don't really have the fluid structure interaction there correctly. Nevertheless, it's amazing how well these models have done. But as I'll show you in a second how they're starting to get limited. But of course, you go to a full 3D model, you're going to need that exascale box. So maybe in a few years I can stop doing that. But right now I still have to use those codes. This is sort of law of unintended good consequences sometimes. When we were doing this, we were big into AMR and doing memory efficient programming so we could use our parallel computers better. It turned out that we did such a good job, most geologists got pretty decent answers on their laptops. So the supercomputer usage really paid off in that way. So no matter what you do, good software tools are always going to be useful. They may not be used the way you wanted them. So our tool is actually more used now online and on laptops than on the supercomputers for which you wrote it for. So more of the details of the modeling, which is really just a depth averaging through the thickness. The entrainment models, I mean, you could sit down for every day of the week, you could write another one and still not come up with a good one. So the sense I want to convey to you that the modeling here is not an exact science. The modeling is very phenomenological, and then what that ultimately leads to, which initially I thought was a disaster, was the uncertainty. The uncertainty is dominant here, and I'll get to that in a second. If you saw my real title, it was the Newton-Bayes framework. So we're still living in the Newton framework here. So all this is good. Of course, multi-phase flow. Pictures are always good. So here's a small version of the big one, which we actually have very well documented, so we can actually calibrate some of our models. Here's the bad news, though. We discovered that after calibrating to this one, nothing works on the big scale. So the scaling laws are all wrong. But nevertheless, so much more detail, of course. Numerically, one had to do lots of interesting things: adaptive mesh refinement, dynamic load balancing. The only dynamic load balancing that I found that actually works for me is a very simple heuristic least square kind of thing. So we keep monitoring the time consumed by each processor and then adjusting the load based on that. So every 100 time steps, we have a sort of a continuing count, keep moving things. And the interesting experience I had is when we first did it, I wasn't quite sure of the code. It kept taking all the elements out of a particular processor. It would move all the cells out. Must be a bug in the code. No. 2 days later, that processor showed memory faults. The processor died. So what was happening is there was a lot of faults. So it was redirecting memory all the time or something. And because of that, the system was just moving load off. So inadvertently, in this dynamic load balancing data-driven process, we actually built in some resilience without trying. But this is a theme that I think has to come as we get to hundreds of thousands of cores. The system has to take care of itself. The application has to be self-healing, if you will. So the mantra here is simplify, localize, parallelize. And that's the only thing that will work. If you have anything global, you're dead. So the more local you are, the more you adapt to your needs, the better off you're going to use the resources. That in of itself is a whole big talk. We had been using these space filling curve type local schemes, and the whole world had been going towards these global graph type schemes. I like the simplicity and locality of these. And then I'm sitting about 2009-ish. Suddenly, one of the NCAR guys walks into me to make a presentation and says, "Oh, we finally figured out how to go beyond 15,000 cores." I said, "Yeah, what did you do?" "Oh, we discovered this thing called space filling curves and local partitioning, and that really works." I said, "Good, thank you very much. Did you cite me?" It turned out that I had published in 99 or something, and it kind of got buried by all the other stuff that came after that. So I had to politely remind him. So being too far ahead is not a good thing. But there are other serious numerical challenges. I don't want to say that this Newtonian domain is all dead. Spurious thin layers, for example. And this, what happens is when you start getting right to the boundary of these shallow water flows, you start getting into a very classic problem. How do you divide small numbers by small numbers? Because when you look at this, you look at the h is the thickness of the layer, hvx is the momentum. To get the velocities for the hyperbolic transport, you have to divide this hvx by h. So dividing a small number by a small number is a difficult enterprise. And what it does is it leads to spurious speeds. Spurious speed then leads to more transport, and you suddenly wick away all the material into a thin, fast, spurious layer all over the domain. So you have this thing that starts moving 100 miles an hour, 2 centimeters thick, all over your domain. Of course, that's wrong. So how do you go after that? So we came up with a whole bunch of, so there's a lot of interesting numerical challenges still left in these calculations. I don't want to trivialize that. There is, of course, I'm not going to talk about it today. We are doing these calculations on representations of the topography. These are all mostly remote sensing stuff that's post-processed. And we did a little experiment where we took 7 sources of these and did these calculations. They could completely be different mountains from the results. So we actually came up with some interesting ways of creating error models and creating ensembles of possible DEMs as opposed to one DEM, and use that in an averaging way to get rid of some of that error. That's, again, a difficult one. So if you want to look up, there's a nice paper in PRS about 2 years back. level sets method. So we're still playing with that interface problem. Now, sometimes a problem can be an opportunity. Let me tell you what I mean by that. So we did level sets method. It kind of worked. Then I went into this new phase field method. So this is all still exploring this problem. The phase field method is very expensive. So first look I had at it, I was like, oh, no, why are we doing this? Then the Snow guys who had abused our model on the GLOF and so on, they came back and told me something very interesting. They said that this entrainment that you're struggling with, in the Snow avalanche, we can document it and show that most of the entrainment happens right at the snout. Okay, so what is the snout now? What is the edge here? In a classical interface capturing method, that's a very, I mean, you can say one layer of cells. One layer of computational cells has no meaning. It has to be related to your flow. And if I use this phase field type approach, I actually have a parameter that is telling me where my interface is and how diffuse and how thick that is. And that I can then use in my constitutive modeling directly to come up with a very good model of the entrainment, something I had struggled with all the time. So when you do these things, sometimes something that turns out to be bad for this turns out to be an incredible opportunity for something. So the entrainment model, which I'd given up on, I have a very good handle on that now. So here's another one. So the shallow water stuff works well, but not for everything. This is a little California Big Sur, just north of Big Sur, I think. So if you want to capture something like this, cliff collapse, this is a very classic cliff collapse. If you build in California, you have to eventually deal with one of these. The shallow water cores don't work. Because once the slopes get above about 60 degrees or so, nothing, they all die. Because the normals are not unique and all sorts of interesting things. So we came up with this SPH type code, which does that. It's not classical SPH, because you do have a very sharp front. So we coupled SPH with the Riemann solver, shock capturing, all of that. That actually works, but it's very slow. It takes a lot more computing cycles. So we're now struggling on how to actually do a problem of scale with it, a real problem, the ones that I showed you, how to do it with this code. Probably a little more computational efficiencies have to be done, so a couple more PhDs before that's usable. But that maybe one more generation of computers also. But that's, this is all still a nice linear progression, I think. There are numerical challenges, modeling challenges, but these are things that we have done for 15, 20 years now. There's still a lot of good things to be done, but I think what really started getting me was the notion of, but I don't know these models. I don't know the parameters. I don't know the topography. I don't know became the theme almost. So if I don't know, what can I still tell you? And this is where this idea of combining sort of Newtonian models to supplement your data and put them into a nice Bayesian framework, that then gives you the correct way of predictive simulation. A single simulation in of itself tells you a few things, but it doesn't tell you what's going to happen in the future. A single simulation can be calibrated, tuned, and so on to do something that replace something that happened in the past. It can be used to obtain some insight into a particular physics, to understand something. But if you want people to go out and build roads and bridges, you want people to decide where to live, a single simulation is not the right way. Because you have to tell them, your probability of being hit by something bad is X. And then let them make the judgment. I want to live with 1 in 1,000 probability of being run over by a car. I'm happy with that. I want to live with 1 in 100 probability of having 10 feet of snow on my roof. No, it's actually 1 in 1 probability in Buffalo, but. So those are choices that people should be allowed to make based on their risk tolerance. And that's what this really should be about. This whole study of hazards has to boil down to letting people make informed decisions, whether it's an emergency manager or somebody who's going to invest in property. And that's what this Bayesian framework allows us to do. So physics-based simulator to explore the possibilities, then calibrate, validate, and predict using the Bayesian methods. That's really where this is all about. Now, this is where we do make a bit of a leap of faith. Even though those models are bad, if we have correctly categorized all the inputs, all the variables, and if I can quantify the uncertainty in those inputs. So for example, in our case, it would be the volume of the flow, the basal resistance, the internal rheology. So these 3 or 4 factors, if I can correctly quantify the uncertainty on that, propagate that to the outcome of my interest, whether it's how much flow at my house, how much flow on this road, then I have done a good job. Then I have given useful information. And I posit that this is the hazard probability that you need. Okay? This is an axiom. I cannot prove it. But if you believe this, I can give you useful information. And if I'm careful about all the variables, all the inputs that affect the output, this is actually going to be good. So that sort of gives away the game now. Here's sort of a historical curve of volumes of flow versus numbers of occurrences. Of course, the small events happen very often. Large events happen infrequently. The good news I've discovered is that, at least for volcanic events, and I'm told for earthquake events, these are fairly standard exponential distributions for the size of the event. Okay, and there is a certain self-organized criticality that's responsible for that. We got data from a couple mountains, and then we moved it to other places. The shape of the probability distribution was about the same. The curves were slightly, the slopes are a little different depending on each mountain. So a couple of observations, and you can certainly have a good distribution for the input, in which you can then sample and go through. But this is, and of course, these are all the uncertainties. But it's not all going to be that easy, of course. To characterize this uncertainty, I need about 1 million evaluations of my model. Of course, that's not going to be affordable even if you are at NCSA. Or even if you are at NCSA, you may not have the money to afford it for every single calculation that you need. This was a small calculation we did that would take about 20-minute calculation on 64 process. So that's a little dated now. But even so, this is still a huge thing. And not only that, typically there's some sort of premonitory event. Somebody observed gas in a volcano. You looked at the seismic charts and you think something's going to happen tomorrow. So everything needs to be finished in a short time. You don't have time to wait in a queue. Now, I understand that there's this, for the hurricanes now, there is a procedure that NCSA shuts down and you guys tack, and I think you guys run everything overnight. But you need much more than that. You need an approach in which you can do better than this, million calculations and petabyte of data. Because each calculation produces a few gigabytes of data. So how do you process a petabyte of data in a couple of hours? So the approach that we first started with, and this is still pretty reasonable, is to not do 1 million calculations, but do a small, well-chosen ensemble, whether it's driven by some kind of Latin hypercube design or the ones that we prefer, quadrature-driven. What quadrature-driven does for you is that it tries to minimize the error in the first and second moments of the output PDF. So you could capture the mean, you could capture the standard deviation, for example, and that really works. This is the famous polynomial chaos of Kadniarakis and company. Modified a little bit, but that's really what we've tried here. The good news about this stuff is it's fast. There are a couple of fundamental weaknesses. Weakness number one is that most of the time, the ones that you really want to be careful about are the tail events here. Capturing the first 2 moments is not going to do it. Okay. The second one is that for certain classes of hyperbolic problems, there is a technical challenge in coming up with the right chaos modes. And that's intractable. So these 2 reasons, I mean, we did a couple maps, and to deal with the tail event, we cheated. What we said is, you saw that curve where I had a lot of data on the small events, right there. So I pretended that all that I was concerned about was this. So I created my PCS ensemble based only on this, completely ignored all this. So that way I sort of tailored it to the tail, but that's really ad hocism. So this approach, again, we've used it, we like it, but it's not going to be the best for the rare event prediction. But we've used it very successfully on the ash plume prediction, for example. Hindcast is very good. I'll show you the pictures. So you see the black stuff is the real ash. The light blue is the 20% probability prediction. The brown is sort of the 70% prediction. And London was way out here. So you could have gone on that flight. They didn't have to stop you. But the models they had, they didn't have this type of calculation. So in some combinations of parameters, those models did predict ash without a clear path forward. So they did the safe thing. They couldn't take a chance with anybody's life. But in hindsight, that was way more economic damage that needed to be done. So the approach that we are starting to push now is this sort of simulator emulator, as we call it. So the Bayesian emulators, you can create them. Gaussian processes are, of course, the most obvious ones. And I'll talk a little bit more in detail about this. Now, we've started to go away from that also, and more about that in a second. But so the standard approach is you create this emulator here, okay? And this error model is fit. But this is not hard to fit now because this is fit with the simulator. And I can create all the simulations I need in the regions I need with a good design. If I don't think I have enough data in some region, I go back and run my simulator again. Of course, I do have to go back and make sure the simulator itself is connected to the real data. The few sparse observations, because one thing that's universal in these things is nobody was around when this event happened, or nobody had the right camera or the right measurement tool at the right place. So that small amount of sparse data I have, I will use that to calibrate the simulation, then use the simulator to drive the emulator, and then the emulator can, that's just a Gaussian processor, a polynomial fit. I can do all kinds of interesting things with that, sample that at will, and get my Monte Carlo simulation done with that. So all of that works fine. Now the surrogates, you can see that crumpled paper there. The crumpled paper is the surrogate. The blue dots are the simulations. So the surrogate does a pretty good job as an interpolator. A surrogate or an emulator is not a good extrapolator, but that's what you have your simulator for. A simulator can explore the regions that you cannot observe, and then the emulator can interpolate in between. So you can do your Monte Carlo type calculation on this surrogate now and get all the properties. Of course, the one interesting challenge that came up that you have to keep inverting this darn correlation matrix. And that's a problem that we have studied for many, many years. How do you invert large matrices in parallel? So I bring back all those tricks back again. And 2010, I think this group at IBM, they did, I still believe it's one of the largest matrix calculations ever. They got almost, I'm going to say about 700 teraflops out of this calculation on a 10 petaflop machine, which is pretty good, by the way. But they did a lot of heroic tricks on a 2 petaflop machine. On a 2 petaflop machine, on a Blue Gene, they got 700 teraflops out of it, which I thought was incredible. But that was all trying to do one of these correlation inverses. Of course, this is a standard trick. Replace your global emulator by an ensemble of emulators. So now instead of inverting this big matrix order n cubed, we have order mn cubed. Standard trick. We've done this with domain decomposition for 23 years now. That's the 23rd DD conference happening this year. So that's the trick here. So you localize, and you have an overlapping localization with this ensemble of emulators. And then you use some kind of a distance-based weighting to put it back together. So the statistical models do work. And you put in all the uncertainty together, the terrain uncertainty, the basal friction uncertainty, the volume uncertainty, and you can come up with nice hazard maps like so. Red is, of course, probability of 1. Blue is probability of 0. This one is for Mammoth Mountain. I don't know if any of you have skied there. Mammoth Mountain, there's a lot of controversy about property values and stuff because they've issued a few volcanic hazard warnings, and every time they do that, the property values drop, so the developers go after them, and wherever they paint a hazard map, somebody goes and paints it over. So they've had a lot of ongoing issues with the social science aspects of it. But part of it has been because the geologists have given very Boolean information. This is dangerous, don't go. If you communicate saying, look, the hazard is 10%. Are you comfortable with 10%? Are you comfortable with 1%? Let people make the call. Then I think it'll be much more rational of a decision. That go, no go, it doesn't work. So this is our pièce de résistance, as we say. There's the island of Montserrat down in the Caribbean. I don't know if any of you are rock and roll fans, but the Beach Boys actually recorded a lot of their stuff down there. That got wiped out by volcanoes over the last 25 years or so. So the good news is the British are very good at record keeping. So they posted a bunch of geologists down there. So they recorded everything that happened for the last 30 years. So all the data for fitting our curves, beautiful. So we came up with this very nice hazard map now for that island. And people still live right up here. There's still some people up there. I think they have a line around here, north of which they don't allow. And the first site of the observatory was right here, which got wiped out. Now they've moved an observatory back here. But those guys are also using some of our tools. But what I like about this is now, in 6 hours, and pretty much just using the processors on our just 1,000 cores. 1,000 cores is these days nothing. And what turned out to be the most interesting challenge, I'm going to go to that in a second, because I haven't talked about data. I've talked about everything but data. They're still computing. Because each of these simulations generates about 2 gigabytes of data. How do I process this 2,000 simulations, each of 2 gigabytes of data in a short time? That turned out to be the biggest challenge. We could finish the calculations in 6 hours, or 2 hours, in fact. And that, so before I go to that, so the inverting those matrices, remember? Multi-level, of course, is the best. And we've just got some, a student just finished up, so we got some very interesting results, the multi-level method, which I think will actually replace or substantially displace the standard Gaussian process approach for doing this, because we have very compact representations now. Sorry, this picture is a little bit bad, but just to show you just the topography representation, this is the representation with 6,552 points. This is the representation using a multi-level approximation in 140 points. And for government purposes, as we say, this is good enough. So for the emulator purpose, this will be good enough. But this is only 140 points. So my terabytes and petabytes of data, I can get most of that with very, very small representations. Okay? And just showing you some more results, and this really works. But getting back to the workflow and this thing. So it turned out that our supercomputers, till the most latest generation of YARCs and so on, didn't know how to deal with data. Never built for doing any data. But the business community, all they've been doing is a lot of data and no compute. Okay, so if you go and buy an IBM Pure system, or what used to be called a Netezza system, it could process a ton of records very, very fast. The way it did that was it had a whole bunch of SSDs, and right on top of the SSD, they parked FPGAs. These FPGAs had in silico programming for pretty much all the structured query language, the SQL code. So anything that would do a SQL query on, which is essentially subsetting the data need not move off the disk. At best, it will move from spinning disk to SSD and be processed right in situ. Okay? Now, so if you try to do the same thing on a cluster, it was a disaster. It's moving all the data through the I/O, never would have happened. So we had to come up with this awful, but I guess clever, now I say, where we do all the data subsetting, all the data processing for this thing that I showed you on this data warehouse appliance. NSF gave us a nice MRI award to get one of those things, but those things are bloody expensive, $5 million for this particular box. And then move for the covariance inversion, we'd ship all that back to the cluster, do all the inversions, put it back on there. So this back and forth just took a lot of clever programming and almost killed a couple of my grad students in the process of debugging. But when we put it all together, that's how we got all that 6-hour calculation done. Moving all that data back and forth and doing the clever processing of there. I mean, in fact, it was kind of funny. The first time we did one of these things on that Netezza box, I mean, typically you start the process and you go away for lunch. This guy did it and it came back. I said, oh, something went wrong. And the student said, oh, no, this is how fast it goes. Because that thing knows how to subset and process data. So that's sort of the overall workflow and showing you some of the numbers of records and some of the, I mean, these are more zeros than I care to count, but these are 150,000 rows. Each row contains about a kilobyte or more of data. Okay. So we have a good plan now. Our old plan of just Newtonian methods has to be now augmented, ensemble methods with good calibration validation. But now we need the hardware, we need the software, we need the tool chain, we need the workflow. We need an entire new environment. And that will happen. It's not a question of if, it's a question of when. We need to direct and focus our energies to have that happen. Okay. Take any questions on that, and if we have a few minutes left, I can talk about my wonderful new PhD program that I was just giving Ed a little heads up on.
I would love to hear about that. So do you want to pull them all together? Do you have a couple slides, or do you want to just talk about it?
Just talk about it. I'll just put one slide and talk about it.
And then we can have questions, okay?
Okay. Let me get that. The common denominator in all of these things, from Netflix to flight simulations to hurricanes, is lots of computing, lots of data. And the bad news is you don't get only computing or you don't get only data. Any problem that's big enough that you compute with a supercomputer is probably going to generate a lot of data. And any problem that has a lot of data, whether it's Twitter or what have you now, also has so much data that by the time you add up even one flop of computing per byte of data, it's a lot of computing. And that's fundamental. That's fundamental. That's how knowledge moves. So how do you come up with students and faculty and so forth that can actually deal with all of this, the data and the computing? So we have finally managed to get through the state of New York system, a new PhD program. I don't know how the state of Illinois system is, but the state of New York is interesting, let's say. But we had to write all kinds of proposals. We had to get external reviews. We had some good friends give us some good feedback on that. And the other thing that I did insist on that we don't want people who can just talk about these things. We want people who can actually deliver cyber tools. Okay, because these are the new scientists/engineers of this domain. If they don't deliver usable products, very quickly they'll not be accepted by anybody. So you are only as valuable as what you do for somebody else. So we have put a focus on actually delivering tools also in that. So let me go back quickly to, so this is the core of the program. Two things I want to emphasize here. One is they all have to start with a master's in a domain science. Okay, and we're still debating whether computer science counts as a domain science, but we'll let that go for now. But it has to, and there's twofold reasoning for it. Ed did say that I started out in this interdisciplinary program, and when I came out, it became an interesting question. Where is my home? Who are my peers? Okay. And when I graduated, it was kind of nice that I had 3 different opportunities. One was in the math department, one was in an engineering department, and one was in a computer science at a national lab. I picked the engineering department, and of course, the money was good. That was one of the reasons. The weather was bad, the money was good. But the main reason was my bachelor's and master's were engineers. So when I went there and I talked to the people, and I talked to the students, I had a certain sense of identification. I said, I can communicate with these people. I can teach these people who I am and what I want to be. When I go to the other ones, I don't think like a mathematician. I can do the mathematics, but I don't think like a mathematician. I'm an engineer who can do the mathematics. And I went to the computer scientist, well, that's another story. So we still figure out what they do. But so that, to me, having a home that is defined by years of study is what is needed. So this is the intellectual home of these people. They'll bring a lot of richness to that home, though. They will be trained in applied mathematics. They'll be trained in high performance and data-intensive computing, and this includes all the database and SQL and information systems kind of thinking also. This is not just talking about big data. This is talking about SQL. This is talking about relational databases and all of that. Because if you want to do something useful in this domain, you really have to deal with a lot of the business data or the unstructured data sets that are out there right now. And then finally, the data science, which is a good name for standard statistical sciences, modeling, Bayesian inference, things of that nature, machine learning, that all sits there. And when you put it together in a nice mix and then layer in a dissertation, which will obviously have a lot of legs in one of these 4. We don't know which one, but each student will be somewhat customized. And then each student will, of course, enter this program with different strengths. Somebody's a math major, they probably have this already taken care of. So we'll have to customize a program to take care of their deficiencies here. Somebody's a stats person, they might need to learn a little fluid mechanics or something. So that sort of balancing will have to be done almost at the individual student level. So the scaling of this program is going to be a little bit complicated. I understand that. We'll need a lot more faculty attention per student than is normal. But when you do all this successfully, I think you will do that wonderful pedagogical thing they always talk about, the T student, a lot of breadth and a lot of depth. I think we'll actually produce those T students out of this. Chip Chukowski, who I think is familiar to a lot of these people in this audience, he looked at this program and he said, oh, I see what you're trying to do. I said, what am I trying to do? He said, you're trying to produce the MD PhDs of this world. And I said, that's as well put as I can say it. Mm-hmm. Okay. And that's what this is about, creating the thought leaders with an integrated training in domain, data, computing, so that they can go back and enrich their domain first, and then each of the disciplines depending on their interest. So we'll have somebody, it'll have to be a special kind of student in a certain sense, because it does place a lot of demands in how they think. Because if you're trained as an engineer, you think a certain way. Then I dump you in a formal computer science theory class on machine learning, you're going to die. Or in a graduate mathematics class, you're going to die. So it's going to take a certain different amount of thinking. The transition will take time. So I want to start off with a somewhat small-sized class, and this is something that we are still fighting our administration about. Administration sees numbers as success. I say, no, quality is success. But that's an ongoing conversation. But I see these people, if we can find the right people to do this and sustain the faculty interest to create something really special.
Thank you. Great. Thanks, Abani. That was great. It's inspiring, I think, for us. So, questions?
Oh. I think I've held them. Uh-oh.
So I have a question on the base framework.
Go ahead.
So usually you have like a very complex stochastic process and many complex applications, right? So I'm curious, how the base framework handles very large number of uncertainties, right? And sometimes you don't even know what your uncertainties are, what you call like unknown unknowns. So, and you don't have prior information because you don't know what those unknowns are, right? So I'm curious, how the base framework will work in those situations.
The unknown unknowns obviously can never be dealt with by definition. But here's what the base framework lets you do. Right. You've done a lot of work with the known unknowns. And as the unknown unknowns reveal themselves, you can immediately incorporate them. Okay, that's the only framework that allows you to do that. You don't have to go back to ab initio. You don't have to go back to zero. You can build on what you know, and you can learn as you go along. So in some sense, that's the only framework I can think of that's capable of handling that. Is it perfect? Of course not. But if you have the right tools available to you, if your codes and software and framework is designed with this thinking in mind that tomorrow, and for us, we had to do that because we don't know what the priority is going to be. Is there going to be gas tomorrow? Is there going to be seismology trigger tomorrow? So we have to think about that a little bit in our problem also. But in the base framework, you at least have the capacity, if you program and plan correctly, of dealing with the unknown unknowns as they emerge. Does that sort of answer your question? We can talk in lunch more detail, but there's a lot of devil in the details in this one. It's not that easy as I portrayed, because going back and doing that, reconstructing that covariance matrix and inverting that is obviously non-trivial. But if you do it the way I was talking about with these small ensembles, many of those ensemble inverses can still be preserved. You only have to look at some of the connections. So there's some facilities you can take advantage of, but it is not a perfect world. It is a tough problem. It's another one. Shawan had a question.
Very interesting, nice work. So I had a question about your mass flow modeling.
Sure.
As you probably know, the National Academy's the Earth Science Resource Board are conducting multiple workshops on landslide risk very recently. It's still ongoing. So I think your work is actually informing that community pretty well. One of the challenges, as I learned from multiple presentations of their workshops, is this consideration of rocks. So I did not see, how you combine the materials of different nature, particularly, these hard materials, gets captured. Could you share some insights in that?
That's a very, very good question. The answer will disappoint you, though. It's, for me, largely not a problem, and let me explain what I mean by that. So it depends on the type of event. So if you're looking at an event like this, so look at the language there. Okay? So these are off a scale. Most of the flows that we have been looking at, these are very large flows. These are of the orders of tens of kilometers, or even at least a couple of kilometers is the smallest flow we look at in this framework. In the frameworks and events you were talking about, for example, the Washington event, that was about 500 to 600 meters. But the volume was such that individual rocks there are also not that good, so we were able to do a good job with that particular event. But when you start talking about this one hillside 10-meter flow, okay, on San Francisco sea-facing villa, that's where the rocks are a problem. Because the rocks, if you want to individually account for the rocks, you need to know where they are. And that level of detail is usually not available. So if you commission a special, you can actually do that. Nobody's done it to the best of my knowledge, but I can think of a framework where you fly a couple of drones and map every single one of those things, and then you can bring them back into your topography and terrain here. And you'll have to figure out, and this is where the grand unknowns are. The landslide, the biggest issue is when will it give? The failure criteria is very heuristic. It depends on soil moisture, it depends on the particular slopes and terrains, the rheology of the material. So a lot of that with remote sensing is shooting in the dark. But that's the state of the art on that. So you can get LiDAR data now down to the centimeter scale, so you can actually see where those things are. And the insurance guys actually would like to know it at the scale of the houses. Talked to a big Chicago-based insurance company, and they said, can you tell us something at the house level? I said, what about zip code level? So, because right now they have, what I told them is, look, anything physics-based you have is now at the county level. I'm going to give you zip code level. They said, no, if it's house level, then we can price it. It's zip code level, maybe. So we're still talking. Maybe we'll come in half a zip code or something we'll agree on. But if they're not of sufficient scale, the modeling I talked about doesn't work. You really need much more data than we have had the luxury of. Because when you talk about sites in South America, you're lucky you sometimes get 90-meter scale data. 90 meters is the size of this room. That's the finest resolution you got. So it's a question, it's a data question much more. And now, yeah, it's possible. I think that's a good research direction to go in, to actually try to get because we can now deal with the size of data. And the modeling can now be done too. Because earlier we just gave up our hands and said, why bother modeling? Nobody will ever give me the data for this. Now the data is possible, so yeah, that's a good direction to go after. Good question, thank you.
Another question? I thought, Greg, yeah.
This one on? Just a quick question. You mentioned, you had an interesting comment about providing software externally and then supporting it.
Yeah.
Have you changed that model? Do you still continue to release the software and have disclaimers about it's up to you to use it correctly, or do you have a new method for support?
I have an SI2 award, so I have to promise to release all my software completely open source and public and frequently. Yes, we do all that. What I'm discovering is that majority of the geologists have zero interest in installing any software anywhere. They were very happy using it on the online platform. The online platform also allows me to have a release every day, if you will. Okay, because that's one, I just have to update one piece of code. That's easy. Before that, when we had hundreds of users all over the country, the support model was really hard. Because you'd get these crazy emails, and some of them were, the answer was, turn on the computer first, please. Okay, I mean, you've all dealt with that if you've supported software. I mean, these are people who are not computer familiar. So you suddenly ask them to do a auto make. It's kind of a problem. So that bridge, we kind of solved it a little bit by only releasing Linux versions for a while. But that's not the right fix. But the online thing is really helping us a lot. The second thing the online thing is doing for us, if we make a bug fix, the amount of testing that the community does for us even before we can get around to it is awesome. So we never realized that virtue of it. Now any bug we put in there is found within 2 or 3 days. Somebody somewhere will break it. And so it's a lot easier. And then there's a sort of reference solutions, reference behavior. So yeah, we do have the classical. We still put out code. You can still download it from the right place. In fact, you can download it right from the online place, from vhub.org. You can download it right there. But the good news is that you can also execute it right there. You don't need to bother if you don't have to.
I have one question for you. I'm curious, as you build that CDSE program, if the existence of such a program now at NSF, which is still growing slowly, but it's there, did it help you legitimize that to your administration? And then maybe the other way around, as you have such a program, can you go to NSF and sort of say, hey, this is really important for us? I mean, can you comment on that?
The first part is 100% true.
Yeah, good, okay.
First part is 100% true. I mean, my conversation started with bringing up the web page on the NSF site saying, this is not a solicitation. This
Right.
is a program, and you understand the difference very well.
Yes.
So I had to explain the difference to them, but that was the beginning point of that conversation. That really helped.
Good.
The second part of going back to NSF and saying, now that I have a PhD program, you should encourage and invest in this, working on that. Not quite there yet.
Too bad we're not there anymore to do it. But
So we have to go back and talk to the new people, and some of them get it, some of them are still struggling with the ideas, but yeah. It's a re-education process that has to happen more often.
Exactly.
So yeah, if you have a chance, please.
Okay, well, we should talk more about how to do that. Okay. Okay, so thank you, Abani. That was great. I think really appreciate it.